Hello. Hello. Suresh.
Dr. Bhaskar, good morning. This is Prabhakaran.
Good morning, Prabhakaran. Can you hear me?
Yeah, it is audible. Nice. How are
Okay.
you?
Okay.
Okay,
I'm good.
okay.
I'm good.
Good. That's fine. It will start at 10:30 at exactly.
Okay. Okay. Sure.
Sure. Thank you. Very good morning to all who are joined in this virtual conference in Recent Trends in Chemistry 2021. Indeed, it's a great pleasure in inviting today's resource and introducing today's resource person, Professor Dr. Bhaskar Sundarraj from Indian Institute of Technology, Kanpur. Dr. Bhaskar did his master's at St. Joseph College, Trichy. Then he did his international master's at University of Wien under the chairmanship of Professor Dixner, the one who was nominated for a Nobel Prize. Then he did his PhD under the guidance of Professor Matthias Ackert and Christian Brunet at University of Wien. Then he moved to University of Max Planck Institute, Germany, for doing his postdoctoral research work with Professor Alias Brasner. Then he did his ABH fellowship too with Professor. After completing his Alexander von Humboldt fellowship, he moved to Indian Institute of Kanpur and take up his position as assistant professor of chemistry in 2013. Now he has been promoted to associate professor of chemistry. As far as his credentials are concerned, he is a recipient of n number of awards: ABH fellowship, Time Chemistry Journal 2014 award, and DAE BRNS award, and so on. So far, he published 66 international research papers in various disciplines, journals, American Chemical Society, JSES, Anglo-Andy, Chemistry European Journal, JOC, TETLET, ChemSusChem, n number of articles having the greatest citation. Recently, you can find the citation of him is 2,858 with a H index of 28 and I-10 index of 40. Such a great, impressive I-10 and H index score Professor Dr. Bhaskar is having. Currently, there are 8 students who are pursuing their PhD and postdoc with the professor. Within this brief introduction, I welcome Professor Dr. Bhaskar to share his expertise with our participant for his convenience for 1.5 hours or whatever he wants to have. Welcome, Professor. Professor, please unmute.
Okay, so thank you, Prabhakaran, actually, for your kind introduction. And let me try to share my screen first.
Okay, please.
To share this. Can you able to see my screen now?
Yes, it is fine.
Okay.
Fine, Professor. Fine.
Yeah. So thank you, Professor Prabhakaran, actually, for your kind introduction, and let me also thank at the outset all the organizers actually for the wonderful symposium, which is started actually on 4th and going on actually till 7th of January 2020. So let me try to give an overview of what we have actually carried out in the last 7 years in my independent career. In particular, I chose to actually give a talk on Cobalt-catalyzed C-H functionalization. And so let me try to convince you during my lecture why C-H functionalizations are important and why do you need to actually work on that particular topic, and what is the need or necessity for us to actually choose cobalt as a metal. So before I actually get into it, let me try to actually give a glimpses of actually the way at which actually we synthesize or functionalize the molecules. right? So if you look at organic synthesis, actually evolved over the period of last 2 centuries, right? So it started with simple aromatic system. So if you want to functionalize an aromatic system, you have to go via an electrophilic substitution reactions, where depends on the functional group on the arene ring. So you will be able to selectively functionalize either at the ortho or para position, or actually at the meta position. So the question always comes, will you call that as a CH functionalization? So let me come to that a little bit later. So, but as far as the textbook is concerned, so we know the aromatic electrophilic substitutions are actually possible. Depends on the functional groups which is attached on the arene ring. So it actually directs at the 2 different sides of the arene ring. Right, so the moment we go with, let's say, for example, an carbonyl derivatives which is attached to the arene ring, so and it actually going to direct only at the meta position, because this is an inherent reactivity which is dictated by the electronic factors which is coming from the functional groups, right? So what happens in case if I want to actually functionalize not at the meta position, but if I have to actually functionalize at the ortho position, will that be possible? If so, can inherent reactivity lead to that particular product? So that what we studied from the textbook, it is not possible. Like, what is an alternative way to functionalize the CH bonds which are at the desired position, rather than actually having rather than coming through this inherent reactivity? So that's the limitations we have with the simple aromatic electrophilic substitution type reactions, right? So can we actually move ahead and see actually how an classical organic synthesis evolved over the last century, right? So typically you have an aromatic ring, so you try to substitute an aromatic ring with either an nucleophile or an electrophile, and then you have to add various reagents, which sometimes are actually good, sometimes actually very toxic. So it depends on the reaction conditions. Either the reaction can be completely automechanic, or it always actually lead to stoichiometric or more than stoichiometric amount of a side product, which most often actually goes as a waste to the environment, right? So then in the later part of 1970s, people started to functionalize the arene ring with a known method to make the halogenation. After that, you try to couple this aryl halides with, let's say, cross-coupling or an organometallic reagent. So thereby you will be able to make the CC bond formation or even a C heteroatom bond formation using the transition metals. And this was kind of a overrule for the last 4 decades, and which eventually got the Nobel Prize for this particular topic in 2010. Right. So what is the limitation of this particular strategy, and why people have to actually move away from this particular strategy, although it is very well established and very well dependable strategy for any type of targeted molecular synthesis. Right. So the problem with the cross-coupling reactions are you have to have the pre-functionalized and organometallic reagent, and at the end of the cross-coupling reactions, you will always produce stoichiometric amount of an organometallic based. Right. So when we talk about, let's say, how to move away from the classical organic synthesis to a metal catalyzed organic synthesis, so you have to also consider the amount of stoichiometric amount of waste which you liberate at the end of the reaction, right? If you do not consider that, then there is no point of creating another catalytic reactions by replacing the traditional organic synthesis, right? That is when we started to ask, probably many chemists around the world started to ask this question: can we try to somehow use the CH bond as a reactive functional group? If so, then we will be able to functionalize the corresponding CH bond into the C functionalized functional group, right? So if this is possible, then one would be able to achieve lot many things in a very efficient and straightforward way, rather than doing the pre-functionalization, which perhaps actually not required. So the advantage of such methods, so where you will have step and atomeconomy, so in comparison with the pre-functionalization required in the classical organic synthesis or in the cross-coupling reactions. So let me take a little bit more into detail. Let's say, when do you call something as a CH activation, and when do we call something as a CH functionalization? Even many people who work on this particular area do not understand this, and they either call that as a CH activation sometimes, or sometimes they call that as a CH functionalization. So one has to understand that actually very carefully. So how do we synthesize typically? Let's say if we get a crude oil, and from the crude oil you do the fractional distillation, you separate your hydrocarbons. Once you get the hydrocarbons, you convert the hydrocarbons into a corresponding reactive functional groups by halogenating, for example, then you convert that into a corresponding another functional group through a classical organometallic reagents, and then convert that functional group into an expected product, right? So this is the classical way one would actually functionalize CH bond into the corresponding C functionalized compound in a sequential manner, right? Each step when you actually do, you will try to actually give the stoichiometric amount of a waste that one has to keep in mind. So what is the alternative way? The alternative way is, can we directly functionalize, let's say, CH bonds into the corresponding functional groups? So if so, I mean, is that direct way is quite easy? I mean, if it is easy, everyone, I mean, have to use that in both in academia as well as in industry. But we all actually know that CX bond is actually quite reactive compared with the CH bond, because there is absolutely no polarity involved when it comes to CH bond. Whereas the CX bond, because of the electronegativity of the X atom, it actually tries to pull away the electron from the carbon towards the X atom. So that's one of the reasons the polarity in the CX bond is much more compared to, let's say, CH bond. Right? When something is not polar and when something is not possible to be reactive, then how can you make it more reactive starting material, right? That is the question actually one needs to ask. So in addition to that, you have another problem associated with the CH bonds. Let's say, for example, if I take a simple alkane, where the alkane contains one terminal sp3ch, and I have actually two internal sp2ch, and I have one more actually internal sp3ch, which are actually given in a pink color, for example, right? You have a three different sets of actually CH bonds available in a very simple, let's say, 6-carbon system, right? So if that actually available as a starting material, so if you try to functionalize it, you have to be extremely selective when it comes to functionalize either at the internal position or at the terminal position, depends on your need. So can one catalyst able to specifically activate one CH bond over the other, which is extremely very difficult. I mean, even now it is actually quite challenging one, right? The another example I would like to take is a simple arene system, where if you take a toluene, for example, or nitrobenzene, for example, right? So if you try to see this particular molecule where you have an ortho CH bond, meta CH bond, and para CH bonds, right? If you are able to go and functionalize this particular compound based on the electronic parameter, then you have to go either via ortho para or actually meta director, right? So you cannot actually go to a desired product if you really go and work to using that classical organic synthesis. So this is a simple molecule. Let's assume actually I've taken a molecule which contains various functional groups. I have a acetylenic CH, I have a benzylic CH, I have an arene CH with which has a possibility of electrophilic aromatic substitution reactions. I have an inert CH bond which is at the meta position, for example. I have a CH bonds which can be possible to activate with using the organometallic reagent. So there are different possibility of CH bonds available in a very small molecule, right? So that's why CH bond activation in a selective manner is extremely difficult. Okay, let me also take it a little bit more in detail so that you will understand when do you call something as a CH activation and when do you call something as a CH functionalization. So keep in mind that whenever a carbon-hydrogen bond converted into a carbon-metal bond, when there is a MC bond formation occurs, that is when you actually try to call that as a CH activation, because the CH bonds are activated by the metal, thereby you create organometallic species in situ. The alternative option, which is actually given at the below, where you have the high-valent metal oxo species or metal amido species. These metal oxo or metal amido species are already high-valent in nature. So it cannot actually go for further oxidative addition because it's already forbidden, or it's high energy process. So where these oxo or amido species are quite reactive, and it immediately react with the corresponding CH bond, either via insertion process like it was shown at the within the bracket, or actually you can have, let's say, the one which is at the bottom where it can go via hydrogen atom abstraction process. So thereby you will be able to form the corresponding carbon functionalization, right? Carbon hydrogen functionalization. But the problem is that in the bottom process, right, so you will not able to see the metal carbon bond formation, right? There is absolutely no metal carbon bond formation, unlike in the case of the top one. So that is why, so the top one people used to call that as a CH activation process, and the bottom one people used to call that as a CH functionalization process. So in more mechanistic way, people used to call that the top one is the inner sphere mechanism, the bottom one actually goes via outer sphere mechanism. Okay, so let me also take it to a textbook level and try to understand actually how the CH activation process occurs, right? So consider if we learn actually from the textbook in organic chemistry. So where you have a ligand, the ligand actually try to donate an electron actually to the metal, right? So CH bonds are nothing but a sigma bond at the ligand, and the sigma bonded ligand actually try to donate a sigma electrons actually to the metal. Thereby, you will be able to actually form the corresponding metal CH bond interaction first. And once you actually have such kind of a sigma donation of CH bonds, CH bonded electrons to the metal, so you will also subsequently have the possibility of symmetry adopted orbital, which is actually going to donate electron from the filled metal orbital actually to the empty sigma star orbitals of the corresponding CH bonds, right? So it depends on the energy level of the corresponding sigma star CH bonds. Okay, so either it can be facile for CH activation process, or it cannot actually be very facile. Why do I specifically say so? Because if you take, let's say, for example, aromatic sp2ch bonds, where the sigma star orbital are very low in energy compared with, let's say, an aliphatic sp3ch bonds, and that is one of the reason. If you really look at the bond energy between the aliphatic CH bond versus an aromatic CH bonds, the bond dissociation energy is more or less the same. The only problem is just non-accessibility of the corresponding sigma star orbital in the sp3ch and make it more difficult for the activation of an sp3ch bonds over sp2ch bonds. So if one has to consider to activate the sp2 or an sp3ch bonds, and both has to go in parallel, and there is then only the possibility of activating the CH bonds with the help of the metal, right? So in the later former process, we tend to call that as an electrophilic. In the later process, you tend to call that as a nucleophilic. Okay, so one can still question, is CH bond activations are something really new, which is in my opinion not, right? So I mean, it's not only CH functionalization, even in chemistry, for example, things are evolved over the period of, let's say, 100 years. It does not actually happen overnight, right? So let's say if you look at actually the chemistry which was explored in the early part of 20th century, that's around 1900, people used to work with organometallic reagent, but in a stoichiometric manner, right? Whatever people try to actually do in a stoichiometric manner in 1900, you will be able to reproduce it. Perhaps actually you will be able to mimic those reactivity in a catalytic manner now, because such kind of an organometallic species are possible. In fact, it is possible to isolate it. If so, can we actually try to make those actually organometallic species in situ? And that is what actually people try to do nowadays actually with the catalytic processes, right? So, for example, Fenton and Dimroth in 1899 showed with the mercuric 2 acetate, right? When we take the mercuric 2 acetate, treat with the benzene, he was able to show there is a possibility of aryl mercury species, right? So his proposed mechanism or proposed pathway is actually going via this valent complex or a sigma complex. So because he proposed that actually this particular mercury acetate actually tend to form such kind of an electrophilic activation, and thereby you will be able to form the aryl metal species. So I keep that actually for a moment, because I'll come back to that in another actually minute. So the second possibility of a CH activation mechanism is, so where you have the CH bonds and you are able to activate the CH bonds in the presence of a low valent metal. Say, for example, you can take a ruthenium 0 or a cobalt 0, for example. So you will be able to make the oxidative addition of CH bonds if you are able to bring the CH bonds to the metal via sigma coordination. Like it was shown in the middle, right, where you can form the sigma complex first, and thereby you will be able to break the carbon hydrogen bond, because there is a sigma donation and the back donation is more from the metal to the corresponding carbon hydrogen bond orbital, and that is one of the reasons the bond length of the corresponding CH bond get elongated, and thereby you will be eventually cleave the corresponding carbon hydrogen bond, and the metal insert between the carbon hydrogen bond, and the oxidation state of the metal actually goes up by 2. So if metal oxidation state is 0 at the beginning, so you will end up in the metal 2 plus oxidation state, which we study in the textbook for oxidative addition process, right? So that is very much possible if your metal is in low valent complex. But if your metal is in high valent, so before I go into high valent, so there is a classical example of a stoichiometric reactions where people start to use this octahedral ruthenium bisphosphine complex. And so where you have a 2 aqua or 2 water, two solvent molecules which is at the axial position, and so when you try to treat with the naphthalene, it immediately go for oxidative addition. Thereby you end up in getting the corresponding octahedral complex, but now ruthenium is in +2 instead of ruthenium 0. And in the similar way, so you can also actually possible to activate the CH bonds in an intramolecular fashion rather than the intermolecular fashion, and that is what actually given at the top right. So And the third possibility of CH activation process is through high-valent metal complex. Why do we need to actually go away a high-valent metal complex? Right? If someone is already established with the low-valent metal complex, we could still continue with the low-valent metal complex because energetically this is a very much feasible process. But one has to also keep in mind that the low-valent metal complexes are not that very much stable, often air sensitive. It is very difficult to handle it sometimes actually in hand. So this is perhaps actually not true, or perhaps actually not. Sometimes it is correct, sometimes it is not correct. Let's say for fourth and fifth row transition metals, but it is very much actually true for the third row transition metals, where the low valent metal complex are extremely air sensitive, right? That is one of the reasons people wanted to move away from this low valent metal complex to high valent metal complex. Thereby, one would be able to do the chemical process that can be applicable to all chemists rather than only an agrometallic chemist, because the middle one is only possible by the agrometallic chemist, but the bottom one can be done by anybody. He does not need to be an agrometallic chemist. He can be a chemist who could be able to actually do this particular process like a classical organic synthesis. So how does this chemistry work? So let's say, for example, if I have a metal carboxylate species which is already in high valent oxidation state, I try to take this metal carboxylate species, treat with, let's say, a arene compound or a solvent arene. So when I try to treat with an arene, so what happens is that the initial formation of a metal arene sigma complex. So thereby you bring the metal in close proximity of the corresponding carbon hydrogen bond, and then you tend to make a 6-member transition state. The 6-member transition state where the carboxylate tend to leave away from the metal, and you are also simultaneously cleaving the carbon hydrogen bond and forming the corresponding hydrogen oxygen bond. So eventually you cleave the carbon hydrogen bond, and then you end up in getting the corresponding carbon metal species and liberate with the liberation of the corresponding carboxylic acid. People tend to call that as a concerted metallation deprotonation process. Although this was very much observed actually by Fenton and Dumroth in 1899, but the mechanism proposed by them through Whelan complex is actually not exactly right. And that is when the credit goes to, let's say, Keith Fenno in 2007 actually from Canada, so who proposed this concerted metallation deprotonation process, which is actually very much accepted actually worldwide for the high valent metal complexes. So let me take a few high valent metal complexes which are already known by us and convince you actually why these particular metal complexes are actually very useful. And so indeed actually these metal complexes are used by many chemists around the world, including actually many researchers actually in India using these actually pre-catalysts in a day-to-day basis for CH functionalization. Right, so one is the ruthenium parasamine dimer, the second one is, let's say, rhodium Cp star chloride dimer, and the third one is the Cp star iridium chloride dimer. So if you look at the periodic table very carefully, so this is actually the D6 system, right? So D6S2, this is basically the D7S2, and this is a D7S2 again, right? So one is a group 9 and the other one is a group 8. So but if you look at the oxidation state of the metal, so ruthenium is in +2 oxidation state, whereas the rhodium and iridium is in +3 oxidation state. So now there is a similarity between the ruthenium and rhodium, which I actually come back to that a little bit later. So so what you actually have, let's say, typically the complex one can isolate it, or you can make it in situ by treating this chloride dimer with the metal carboxylate. For example, potassium acetate or sodium acetate, you treat that actually with the ruthenium dimer or a rhodium dimer. So you should be able to make the corresponding ruthenium or rhodium diacetate complex. This is more or less well established. People actually try to isolate this complex as a pre-catalyst, or one may also make it in situ. So, and people also did actually a lot of kinetic studies, and they showed indeed that this particular diacetate complex in a neutral form available, or in solution it can also, let's say, in equilibrium with a cationic complex, and thereby you create a vacant site, and that vacant site creation is very much important actually for the substrate to come in. So once the vacant site is created, the arene actually comes in and forming a sigma coordination, so thereby you form such kind of a 6-membered transition state like I showed in the previous slide, and thereby you make the CMD process and liberate the carboxylic acid as a side product and get back your organometallic species, which is very reactive, and you can form it in situ. So like I said, ruthenium and rhodium actually has some similarity. What is the similarity? So where ruthenium-2 and rhodium-3 are both isoelectronic as well as isolable. How do I say so? Ruthenium-2, it is a D6S2 system where you remove the 2 electrons, so you end up in getting the D6 system. And the rhodium-3 or iridium-3, it is a D7 actually S2. where you remove the 3 electron, so you end up in getting the D6 system. So both are D6 system, which is isoelectronic. And in the case of rhodium as well as iridium, so you have the C pisa sitting at the top. There is 6 electrons actually given to the metal if you are counting with the ionic method. And in the case of ruthenium, where you have a arene parasamine actually sitting at the top, and again this structure wise, these two actually has a similar structure. That's one of the reason people tend to call ruthenium and rhodium, ruthenium 2 and rhodium 3 as isoelectronic as well as isolable. Right? If this is really true, right, where rhodium and iridiums are falls in group 9. So, and the third row transition metal for group 9 is, let's say, cobalt. Can I actually try to prepare a cobalt 3 complex instead of rhodium and iridium 3? If so, can I mimic the similar reactivity which was achieved by rhodium and iridium 3, or can cobalt 3 itself have a unique reactivity in place of rhodium and iridium? Right. So I will come back to that unique reactivity a little bit later. So. So people tend to call this third row transition metals, which are earth abundant. It is actually widely available. Most often it is non-toxic, and so people tend to call that transition metals as base metals, and that's why I call that as why base metals. So what is known, and what are the learning which we actually try to get from the data which is available in front of us. So first and foremost is a price. Let's say, for example, if you want to actually work on such kind of noble metal catalysis, so you need to have a lot of funding to begin with, right? Because these metal catalysts or metal precursors are not actually very cheap. These metal precursors are super expensive on one side. Why is it super expensive? Because their availability on the earth crust is very, very minimum, right? When the demand is more, when the availability is less, obviously the cost will actually increase. And that's one of the reasons you will actually see the rhodium, ruthenium, platinum, palladium. So look at it, it's all like in 0.015, 0.005, 0.001. It's a very meager amount available on the earth crust. So if you start to develop a process with these metals now, let's say, for example, assuming that in 10 years down the line, your process are actually going to be in industry, and perhaps it is a very useful process, but unfortunately, 20 years down the line, the process will exist, but the source actually for that particular process actually may not exist. That one has to keep in mind. So that means that even an industry wanted to invest on your process, look for actually the process should be available for next 50 years or 100 years rather than actually working with something actually for 10 years, because that is not actually going to make a profit actually to the industry. On the other hand, if you look at the 3D transition metals, the availability on the earth crust is enormous, right? And that's one of the reasons even nature prefer to actually work with the 3D transition metals rather than actually 4D and 5D, because nature knows how to actually do things in a very sustainable manner. Right, so this is actually very much now noted actually by chemists as well as, let's say, most of the scientists, and that's one of the reasons you see since 2013 or 2014 the number of publications which actually come up significantly, especially on this particular topic. It's purely because you have to actually now move forward. You cannot actually keep on working with this noble metals, although it is easy and the reactivities are well established. And you can actually make a publication, that's not an issue, but will that actually going to be practical in next 100 years? I'm not really sure. So now actually let's try to actually move towards cobalt. I will actually try to convince you why we chose to actually work with cobalt. So before actually I move into that, so I wanted to actually cast to you what is known in the literature before. Like I said, if I have to invent something new, really new, I need to know what is the history behind. If I do not actually know my ancestors' history, so then I cannot actually make a history for myself or my predecessors in the past and in the future generations in the future, right? And so it is so important actually that what is known in the literature, what was actually achieved in the past. If you know that, then you will be able to give your own innovation in that. So here is a stoichiometric reactions which was actually done by the low-valent cobalt complex. I emphasize the oxidation state. It is the low-valent species. It's a cobalt-1, right? So when you take a cobalt-1, as I said, if you have a low-valent cobalt or low-valent any metal, so which will tend to go for oxidative addition, like you clearly see. So and on the top you have the corresponding cyclometallation with an azobenzene, and you have the cyclometallation with, let's say, ketone or a thioketone. You can also actually do with the pyridine-directed CH activation. So in all the cases which you are shown actually in this particular slide are all actually going through the oxidative addition process where the formation of a cobalt hydrate is inevitable. which means the cobalt oxidation state goes from cobalt 1 to cobalt 3. So what about high-valent cobalt? So unfortunately, the high-valent cobalt was never being explored until 2013, and that's exactly the time which I started my independent career at IIT Kanpur. So there were a couple of actually complexes which were very interesting actually to me. So this is the complex which was isolated in 1971. This is the CP star cobalt 3 complex, and another one is the CP star cobalt diiodide complex. And these two complexes are very stable. One can actually make the complex without any much trouble. You can put it on a column chromatography. You can isolate it through a column chromatography under air, and absolutely no problem. Okay, so what is the advantage? So if I actually develop this particular process, anybody can use it. One can also use it in actually, let's say, Coimbatore. One can also use it in Melbourne, and one can also use it in California. And that is the advantage of actually using such an air-stable catalyst. And you do not need to be a skillful person actually to do this particular preparation of this particular catalyst. So this catalyst can be done actually by an undergraduate students in our lab. So the second actually catalyst which I would like to emphasize is the CP star cobalt 1 diolefin complex. This is extremely air sensitive. This particular complex is stable only at -40 degrees Celsius, and if you come to room temperature, the complex tends to decompose. But this is one of the extremely useful catalysts for hydroxylation chemistry, and this was explored for catalytic application by Boris Bruckert in 1997. And after that, there is absolutely not much exploration in terms of, let's say, C-H functionalization. So basically, this catalyst was used actually for all cycloaddition type reactions. So like I said, the cobalt 3 was isolated in 1971, but never was actually used for any applications. But you know, in later 2005, so where the uplift of rhodium 3 and iridium 3 will clearly give an indication to anyone that, you know, one can also use cobalt 3 in place of rhodium and iridium 3, so which will be much more economical, and perhaps actually this is going to be very useful and sustainable process actually than the rhodium and iridium 3. And so if chemistry has to work, it has to actually go via this initial formation of the diacetate, which then actually equilibrium with the corresponding cationic complex. So thereby you will be able to have one vacant site, because this is a 6 coordinated species where you will be able to attach the substrate actually to this particular cationic complex. Okay, so that brings our research portfolio in IIT Kanpur. So we are actually working on a diverse areas, which comes under 3 major themes. One, we consider that as a mechanism, so where we try to develop a ligand on our side, so which can be sometimes fancy only for the purpose of structure. Sometimes actually we design a ligand based on the reactivity which we would like to explore. And once we design such kind of ligands, we try to actually make the complex. We prefer most of the times the high-valent metal complex, because the exploration of such high-valent metal species are not actually possible. In addition, it is actually air and moisture stable, and that's why our catalyst can be useful for many people. And often we try to go either with the results to theory people to get some insight, or we actually have some concept or idea in our hand. We try to actually understand the reactivity before we actually do the experiment actually through DFT calculations. So, but any reactions which we try to do, we always actually make it a point to understand fully. We do not actually want to work on the peripheral. In addition to that, because I was a trained organometallic chemist, at the same time, I mean, more emphasis on catalysis. So that is why I never consider any metal complex as only a metal complex. I consider those metal complexes as a catalyst, and so that can be useful actually for a wide variety of applications if one design a catalyst in an appropriate manner. Of late, especially in the last couple of years, we also started to work on more environmental and social impact applications, which perhaps actually I will talk at the end of my talk in a couple of minutes. So as I said, our emphasis actually focus on 3D tensor metals, actually not on 4D or 5D. So we initially start to focus on iron, cobalt, and nickel. Now we expanded now actually to a wide different actually variety of metals with the 3D role. So like I said, so 4D and 5D are very much useful, used actually by many chemists. Still there is a lot of demand, but 3D metals are not much explored. In addition to that, we teach all the time to an undergraduate or a master students, right? So whenever the 4D or 5D tensor metals, so the 4D or 5D tensor metals, because of the larger size, it most of the time actually prefer to go via 2-electron process, okay, rather than one electron process. And in addition to that, so when compared with, let's say, 4D and 5D, 3D tensile metals, it can either go via one electron process or a two electron process. So one would actually say, oh, that is complicated, because if it goes via one electron process, then how do you prove this is actually the right mechanism? So, I mean, sometimes it is better to take the complicated process and try to understand, which will actually give a lot more insight actually than afraid of actually taking such kind of a topic. So, so this is advantage for me. I take that as an advantage. Okay, so when a metal have the multi characteristic within as an inherent property, I would rather actually take that particular metal and then try to explore either one electron process or a two electron process, depends on my need, right? So that's why I feel 3D tensile metals are much better compared to 4D and 5D. And so that is what exactly the nature also does. Let's say, for example, if you want to selectively convert the CH bond into the corresponding C hydroxylation, where the nature actually does a one electron transfer process in a tandem manner. Okay, so thereby you will be able to functionalize one CH bond selectively over the other CH bonds. So that's the reason actually we question ourselves: can modern alchemy metamorphose the function of base metals to surpass the precious tensile metals? So cobalt, why cobalt? So cobalt is a D9 system, so you know very well one electron actually from the D9 system is very easy to kick out. So thereby you will be able to make the cobalt-3 system in a very reactive manner if you are able to perturb the electron, which is available as a single electron, not as a paired one. So it is very small in size, so it should be quite different in terms of property compared to, let's say, rhodium and iridium. So you take the electronegativity again because of the smaller size, so it should be different in terms of electronegativity with rhodium and iridium. And cobalt being a small size and high-valent oxidation state, it is going to be extremely hard in nature compared to rhodium and iridium, which is actually going to be extremely soft in nature. So one can also ask, these are all the fundamental properties. I mean, how does this property matters, and why do we need to worry about it? So, I mean, if you start to worry about it, then you will be able to find many new reactivities. Let me actually come to that in a few minutes. So, well, the advantage actually, I explained to you what are all the advantages. Disadvantages, people always think cobalt is at a low valent oxidation state very often air sensitive, which is true. And so cobalt at high valent oxidation state never be very active for catalysis. So that's why you need to start with the cobalt-2 or a cobalt-3. You add stoichiometric reducing agents, for example, magnesium. And so when you are using the magnesium, then you will be able to make the cobalt-3 to cobalt-2 or a cobalt-2 to cobalt-1 or cobalt-2 to cobalt-0. So thereby you will be able to make the in situ low valent active species, and that is the one very reactive for catalysis. And this is the kind of a belief people had over the period of 4 decades. So that is why I started to question why one has to go via always a low valent species. Why not actually go via high valent pathway? So I started actually compare the organometallic species, which is already isolated in the literature. Try to understand the fundamental property between the rhodocycle versus cobaltocycle. So if you look at the bond length, especially for example the bond length actually between the cobalt and the carbon versus the rhodium and the carbon, the cobalt carbon bond is extremely short in nature, like you see at the bottom left. It is actually 1.94 versus, let's say, the rhodium carbon is actually about 2.03. This is actually short enough to give a different characteristic of the carbon compared with the rhodium because of the short nature of the bond between the carbon and the cobalt. So this is as good as actually the nucleophilic nature which you observe with the Grignard reagent, right? If you take the methyl magnesium bromide, right, so where methyl become more nucleophilic, right, because of the very short actually bond between the methyl and the magnesium, and that is exactly the same kind of a nucleophilicity you will observe with the cobaltocycle, where the carbon connected to the cobalt are going to be extremely nucleophilic, and that's one of the reason cobaltocycle or a cobalt organometallic intermediate should actually give a unique reactivity compared to the rhodocycle. Okay, so if this is really true, okay, so I will try to actually convince you with some examples. So like I said, the high-valent cobalt species came into existence in 1971. So almost it was in the dormant stage for 4 decades. And around 2013 and 2014, and there were a couple of reports, actually one from Japan and one from US actually came. and using the CP star cobalt as a catalyst, and they were using all the time pyridine as a directing group and try to actually functionalize ortho CH bonds in a very selective manner. There were a couple of actually problems at this particular point. One, they have to actually use 130 to 140 degrees Celsius all the time, and they have to use DCE as a solvent of choice, and they have to use a silver salt because when they ionize the neutral complex into cationic complex, the reactivity become better because the catalyst become more electrophilic. So this is where actually we came in, and we say, oh, if you actually start to use pyridyl as a directing group, and there is nobody actually going to take your method, because it's not actually going to be useful, because it's very difficult to pick out the pyridyl after the functionalization, right? So we take a simple quinolene N oxide, for example, and try to see we can avoid the silver salt first. Can we avoid the DCE as a solvent? Can we try to actually lower the temperature if possible? So that's where we started. We actually tried to take this particular N oxide as a starting material and coupled with an alkyne. So the idea was actually, can we try to do an alkylation here? But to our surprise, it is not actually giving the alkylation. It is actually giving the alkylation followed by oxygen atom transfer from the nitrogen to the carbon, and thereby you end up in getting this beta-aryl ketone. So, and the reaction is quite general. So that's optimized reaction conditions. A wide variety of alkyne can be useful. So many different actually functional groups can be available at the peripheral site of the arene, and so it does not actually disturb the functional group at the peripheral site. So it is always actually trying to give the reactivity at the CH site, not at the C2 site. That clearly indicates that although C2CH bonds of the quinolene N oxide is more acidic, but it is still preferred to go via 5-membered organometallic species rather than actually activating the C2CH bond, which will eventually get 4-membered organometallic species, which is thermodynamically not much stable. So the another beauty thing which we actually observed in this particular chemistry is, so the moment you start to work with the symmetrical alkyne, absolutely no problem, okay, because you are going to get only one product. If you start to actually use an biased alkyne, when I say biased alkyne, you have one side, let's say an arene, the other side, let's say an alkyne. So one is an electron withdrawing group, the other one is an electron releasing group. So you will have the two different type of partial negative charge or a partial positive charge on the acetylenic carbon, right? So because of which, what happens is the insertion process of this alkyne between the metal and the carbon are going to be either at the 1,2 or at the 2,1 type. If that happens, so then you will be able to actually get two different type of regioselectivity, right? So this is where most of the times when you use an unsymmetrical alkyne, so you will end up getting, let's say, the ratio of two different isomers, 1:1 or 1:2 type. So, but surprisingly, in our case, in this particular experiment, so where we will be able to achieve one single regioisomers rather than the two regioisomers, and in addition to that, we are also delighted to see the reactivity with the cobalt is far superior compared with rhodium and iridium. For example, if I use an electron-rich alkyne, so that clearly indicates to me that cobalt indeed actually started to give a different reactivity compared with, let's say, rhodium and iridium. Of course, this is actually almost at the early part of actually the exploration of cobalt in high-valent oxidation state, and many people have started questioning, why do you say cobalt actually give a unique reactivity? So, and we need to convince actually with more and more evidence, which eventually we did after the initial examples. So then one can actually argue, how do you actually explain this particular selectivity, right? So why, where the alkyl group are always actually at the alpha position to the aryl, whereas the aryl group are always at the terminal position. So why it cannot be reversed, right? So that can be clearly explained with a simple way. For example, if I have an arene at the top, so where I have a clear conjugation of actually the pi bonds actually from the arene to the quinoline ring, and that is one of the reasons this is actually very highly stabilized actually with the pi conjugation. Whereas if I have to reverse the selectivities, then I have to actually spend about 11.3 kilocal energy. So that's one of the reasons. So the reverse regioselectivity is actually less favored compared to, let's say, the aryl at the terminal position. So the second question actually asked by us is why do you actually have a different reactivity with respect to cobalt and rhodium, and especially with respect to electron-rich alkyne? So when we did the DFT calculation, where we tried to actually study the ligand to metal charge transfer and see how much actually it differs, let's say, with respect to electron-rich alkyne and cobalt versus rhodium. So let's say when you actually take the ligand to metal charge transfer, there is absolutely no problem in terms of ligand to metal, whereas metal to ligand charge transfer, it is in terms of, let's say, cobalt, especially if you use the electron withdrawing alkyne. But when you use an electron rich alkyne, if you see at the bottom row right side, where you have cobalt gives 27.5, whereas the rhodium gives actually 19.5. So which means rhodium actually give a very lower ligand to charge transfer compared to, let's say, cobalt, and that's one of the reasons cobalt gives a very high product formation with electron rich alkyne compared to, let's say, electron poor compared to rhodium. So if this is really true, like I said, so one would actually form such kind of an organometallic species, right, which is actually, let's say, the 5-membered organometallic species. So then one would be able to couple that actually with an olefin instead of an alkyne. Again, that is a pi donor, right? So then you will be able to form such kind of an intermediate. So that eventually go for an insertion between the metal and the carbon. If that happens, you will end up in getting such kind of possibility. Or the alternative possibility is that where the bottom one, where the metal and the hydrate comes on the same side, on the top one, metal and the hydroxy comes on the same side. So when I actually explained the cobalt, I told you cobalt is very small in size. The high-valent oxidation state, cobalt is going to be extremely hard, right? So we know very well based on the HSAB principle, right? Hard goes with the hard, and the soft actually goes with the soft. This is really true. Cobalt preferentially going to pick out the corresponding hydroxy group instead of hydride. So thereby you will end up in getting the corresponding allyl product, right, rather than reverse product. So let's assume in place of cobalt, if I use rhodium, so the rhodium should actually selectively pick up the corresponding hydride instead of hydroxy. If that is really true, then I will end up in getting the corresponding enol form that eventually tautomerize into a ketone, right? Under the same conditions, just by changing the metal, you will be able to defer the reactivity because the reactivity is not the reactivity, the selectivity, because the product which you obtained with the cobalt is different than actually with the rhodium. Of course, this is the DFT calculation to begin with. So we have actually made the DFT calculation with rhodium, for example, and see how much energy requires for a beta hydride elimination versus beta hydroxy elimination. Please keep in mind that the beta hydride eliminations are very well established elementary reactions for over the 50 years. But when it comes to beta hydroxy elimination, it is not actually still established, and it is not even included in the textbook reaction. So when someone actually proposes beta hydroxy elimination occurs, one has to have a proper evidence. Otherwise, people may not agree with. Okay, that is where we need to study this in detail. Right, so when rhodium actually goes for a beta hydroxy elimination, so the energy required actually for beta hydroxy elimination is about 5 kilocalories per mole, higher compared to, let's say, beta hydride elimination. One could still argue 5 kilocalories is still relatively lower energy, but still 5 kilocalories is required actually to achieve such beta hydroxy elimination, especially with rhodium 3. Right. Of course, this is DFT. One can always argue, okay, DFT calculations perhaps actually true, perhaps not in the experimental observations. So since we have done that DFT calculation first, we wanted to now validate in the experimental process, which is often always very difficult, because if you have an experimental results, you will somehow actually find the DFT validation, but the reverse is always very difficult, unless if the chemistry works in the manner at which actually you think about it. So let's say, for example, if I use a hard nature of corresponding cobalt, right? So the quinoline N oxide actually treating with an allylic alcohol, it's try to give the selective allylation product, so via beta hydroxy elimination, right? So let's say, for example, if I use under the same reaction conditions instead of cobalt with rhodium, then I should be able to actually get the corresponding allylation product. But unfortunately, I do not actually change anything else except the condition, except the metal, right? So when I actually change the metal from cobalt to rhodium, so I end up in getting the corresponding beta-aryl ketone product rather than the allylation product. If you look at the conditions, it's exactly same. Okay, so this very much actually validate what we propose, and we try to actually see the scope of the reaction. So on one side you get the corresponding allylation product, on the other side you get the corresponding beta-aryl ketone, right? So this indicates that cobalt indeed gives a unique reactivity compared to rhodium. So that's the proposed mechanism we have, and so we do actually have some evidence actually for this particular proposed mechanism. So where initially you form the corresponding cobalt cationic complex, and that actually bind with the N oxide, you form the corresponding metal in close proximity to the CH bond. Eventually, you activate the CH bond via CMD process, and you make this Coimbatore cycle. Olefin comes, coordinates, insert between the metal, and depends on the metal. If it is cobalt, you go for a beta hydroxy elimination. If it is rhodium, you go for a beta hydride elimination. That eventually gives the two different products. So the beta hydroxy elimination, is it actually true for only allyl alcohol? Can I actually go for a different type of compound? So let's say, for example, if I take a simple alkyne and I try to actually, I try to show that indeed actually you form the Coimbatore cycle, and the alkene comes, coordinates, you form the metallocycle, 7-membered metallocycle, right? This is proposed, right? How much actually are you really true of what you are proposing, right? Quite often people propose, sometimes it is valid, sometimes it is not actually valid. So for example, people do actually propose such kind of an intermediate for an alkylation process, and where you have the intermediate which is there at the right side, and that will go for a proto-debutylation, you will end up in getting the alkylation, right? So if you look at the starting material versus the product, so it is alkyne insert between the carbon and the hydrogen, you end up in getting the corresponding alkene inserted product. And so because this topic is quite new, not much actually known in terms of mechanistic understanding, we try to isolate the intermediate, and that is the intermediate we isolated, where it forms the 7-membered alkenyl intermediate, and that eventually lead to the expected alkylation product. Like I said, if the beta hydroxy elimination is possible with allyl alcohol, then one would also actually make such kind of a beta hydroxy elimination using a propagyl alcohol, where the R1 and R2 in the propagyl alcohol, if you have a methyl group, that it forces the hydroxy at the same side of the metal. So like you know, the thumb rule is, if you want to eliminate a beta hydride or beta X elimination, it has to be the same side. It has to be a syn coplanar. And when it is syn coplanar, then you should be able to cleave the corresponding X bond, right? So in this case, this is a hydroxy and eliminates that, eventually lead to the alene product, which is very difficult to access in one-step synthesis. So we also eventually isolate the intermediate under the standard reaction conditions, but in stoichiometric manner, and we were able to trap the intermediate which was proposed in our reaction mechanism. And the bottom case, where we are able to show that the moment you actually change the R group from R1, R2 to, let's say, a CH2, so then you have the possibility of hydroxyl group either will be on the upside or on the downside. It depends on the up or down. So you will be able to either selectively pick up the beta hydride or a beta hydroxy elimination, so under the different reaction conditions. And that's where actually we show here the steric plays a crucial role for a beta hydroxy elimination. When you remove the steric, then you will be able to get the corresponding beta hydride elimination. And here we propose the mechanism. So when the intermediate actually goes via beta hydride elimination rather than the beta hydroxy. So let me also take a couple of sp3-CH activation. Like I actually said before, if you look at the bond dissociation energy of sp3-CH versus sp2-CH, for example, if I take an ethyl sp3-CH versus, let's say, allylic sp3-CH or even a benzylic sp3-CH, it's not actually much difference. But as I said before, it's not about the bond dissociation energy alone important. It is important, but it's not only that, right? It is all about accessing the high energy sigma star orbitals in the sp3-CH by the metal orbital. If you cannot access that, then you cannot actually backdonate your filled metal orbital, and you will be able to coordinate. When you coordinate, what happens is that your cobalt comes in close proximity to the CH bond, and thereby you will be able to make the metallocycle by activation of CH bond, and then followed by functionalization, you get the corresponding CH functionalization product, but not with sp2, but with sp3. So we did actually spend quite a bit of time, and we found right conditions which were able to do the corresponding alkylation of the CSP3H bond, and that eventually lead to the 8 allyl phenol product. It's not necessary necessary that you need to use only internal alkyne, you can use the terminal alkyne. So that 18 electron complex, we are able to have a two different scenario, where in one of the scenario the carboxylate bind with the metal, and the another one is the carboxylate stays outside the coordination sphere as an anion, right? So the carboxylate bind with the metal, abstract the CH proton, and that goes out, and that is what we saw so far with the sp2ch bond activation. Right? If a carboxylate is actually comes outside the coordination sphere, it is nothing but the base comes outside the coordination sphere, picks up the proton, and goes out as a carboxylic acid. And we try to actually do the DFT calculation and try to understand the energy difference between intramolecular base-assisted deprotonation versus external base-assisted deprotonation. And is it actually going via the similar pathway like we observed with the sp2ch activation, or it is actually going via different pathway? And we observed that it is the sp3, it is the base which is outside the coordination sphere taking the CH bond much lower in energy compared with the carboxylate which is bind to the metal, and that is actually going to abstract the CH bond via CMD process. And so this is one of the very important actually work by us, and this was actually very well absolutely appreciated actually around the worldwide, because until that point people try to propose the mechanism most often via CMD process, but they do not actually explain to you whether the CMD is intramolecular or external base assisted. So once you form the corresponding Cobalto cycle, this Cobalto cycle will further actually bind with an alkyne in a predefined manner, and thereby you will be able to insert the alkyne between the metal and the carbon, and followed by alkynyl intermediate which goes for a proto-demethylation, gives the expected product. So because we know this this particular cyclomethylation species is possible, this is an intermediate C at the bottom right. If it is possible, then one would be able to actually couple with a different coupling partner rather than only with an alkyne. So we thought of it can take an oxazolone, which can be a very useful coupling partner to form the CN bond formation, where the insertion of the nitrine species which form in situ between the metal and the carbon, so thereby it gives the corresponding CN bond formation upon proto-demethylation. So you will be able to use a wide variety of aryl or an alkyl oxazolone that will eventually make the CH3H amidation product. So the mechanism goes in this way. So where the cyclomethylated species B interacted with the oxazolone via coordination of nitrogen, followed by CO2 liberation, gives a nitrine species, and that eventually insert between the metal and the carbon, you form the amido species, and that will lead to the expected amidation product with the liberation of the active catalyst. So pay attention. So I'm using the sp3ch, which is at the benzylic position. One can argue benzylic positions are very reactive, but to be very honest with you, it is not really very reactive. And so, but then the question comes is that can I actually put an R group instead of actually simple benzylic? And what happens actually if it is an R group attached to the corresponding sp3ch of the terminal position? So then it becomes the internal sp3ch rather than terminal sp3ch. So which means it is very difficult to activate the internal sp3ch in through metal catalyzed process, whereas at classical organic synthesis it is very much possible because of the stabilization of carbocation, right? But here you don't actually go via carbocation. That is why internal sp3ch bonds are extremely difficult. So when we doing this process, actually there were a couple of reports actually came, one from US and another one actually from China. So in both the cases, what they try to show is that they try to use a simple cobalt acetate instead of CP star cobalt, and they try to actually use a bidentate chelation rather than the monodentate chelation, because we know 3D metals it prefers to go for a large number of coordination number compared with, let's say, 4D and 5D. So that's why they actually decided to go with the bidentate chelation rather than monodentate chelation. So if you look at these two reports actually very closely, so it has to go via this particular intermediate if at all the product formation occurs, right? So if these particular intermediates are possible in situ, then one would able to actually insert more reactive gaseous reactants such as carbon monoxide. So that's why we thought actually, let's say I take this particular starry material, I do the reaction under the classical conditions. If I able to actually form this cobalt-3 intermediate in situ, then I should be able to, let's say, insert the carbon monoxide between the metal and the carbon, and that eventually lead to the corresponding succinimate product. And that was the original thought process from our side. So we thought actually we tried to optimize it, and indeed actually we got the expected optimized compound in a very good yield. So this is a standard optimized reaction condition by us. So there is a question actually. So the CO atmosphere we use is actually basically 1 to 2 atmosphere pressure is absolutely no dangerous, and you can also use it in your own lab with the CO balloon without any trouble. But if you look at the reaction which was originally done by Murahasi in 1955 or 56, so he has to use low-valent cobalt, no problem, right? So you can buy the low-valent cobalt which is commercially available, but you have to use CO 150 bar pressure, and you have to do the reaction 20 minutes at 190 degrees Celsius. It's as good as actually having a bomb in your fume hood, right? Because 150 bar pressure of CO is very dangerous, and any small leakage of CO gas is good enough actually to make you to die immediately, right? So that's why it's very important that you develop a carbonylation process under mild conditions, if possible, actually, let's say with an atmospheric pressure. So this is itself is already a big achievement for us, because you don't need a 150 bar pressure. It's only the CO 1 to 2 atmosphere. The only difference actually between the former and the later is in the case of actually our carbonylation of an sp3CH, we use a high-valent cobalt, and in Murahasi case he has to use a low-valent cobalt. The reaction is quite general. I do not actually want to spend time on the generality of the reaction. So one can achieve spirocycle, one can actually do CH activation with a large variety of substituent. One can still actually argue why all the time you need to have the tetrasubstituted carbon alpha to the carbonyl. Is it necessary? Not really, but if you have it, it is better. But without that also it works. For example, if you take a simple cyclopropyl group at the alpha position to the carbonyl, it also works. And if you take a simple propanamide, it does actually works, although the yield is low. And if you take an isopropyl group instead of a tertiary group, it does actually works. So, and that is why I'm saying, so it's not necessary, but if you have a tetrasubstituted carbon, maybe it is better. And so if you look at, let's say, the internal sp3CH bond one at the right bottom, right, which was very difficult for us with the CP star system, because it is not actually giving any product, where here it is actually possible by us actually to activate the internal sp3CH bond, which is actually quite interesting by us at that time. So the obvious question comes, okay, sp3CH activations are possible. You can insert actually CO gas, but can we try to insert CO2 gas, right? If I try to do that, I try to actually do a thermodynamically unfavorable process into a thermodynamically favorable process. How do I do this? So I try to convert the unreactive CH bond into an agrometallic reagent, which is extremely reactive, in situ, of course. So I try to convert the CO2 gas into CO via deoxygenation. Again, CO2 is inert, we all know very well, whereas the CO is actually much more reactive gas, right? If I actually try to do these two inert substrates into inert actually gaseous starting material into the reactive intermediate in situ, then these two reactive intermediates should actually couple each other and then actually form the corresponding product. But the problem comes is that the reaction conditions which I use for the selective deoxygenation of CO2 to CO may or actually may not be suitable actually for the corresponding carbon hydrogen bond activation. Right, and this is where the difficulty comes actually when you wanted to couple the thermodynamically unfavorable process into the reality, right? So this is where actually I got inspiration actually from this particular site. So this is a site which is available in Germany, where 133 companies are situated in one particular place, and this is still exists. This was actually originally used by German in 1930s or even before 1930s, that is before Second World War, and they were very much actually using this particular plant for various war-related chemical weapons, right? So after that, they do not need this particular plant, and they don't want to actually give away, so they decided to actually give it to various companies. The only restrictions actually they have is that there should not be any waste come out of this particular chemical industry. And you can see the river actually which is going beside the corresponding chemical industry, and there won't be a single waste of actually chemical goes to the river, and the river is as clean as you actually see in Rishikesh actually in northern part of actually India, right? It's clean water, right? So which clearly indicates that there is absolutely no waste actually goes out, right? How is it possible? There are 133 companies are situated in this particular place, and you can clearly see there is a pipeline actually goes from one to another, right? So in between the buildings, there is a road, and then adjacent to the road there are actually pipelines actually goes on, and these pipelines are nothing but the raw material actually goes from one company to another company. Why do we say so? So let's say I actually try to create one particular product through a chemical process, and I am actually getting the expected product which I require, and I am also producing simultaneously, let's say for example, 1 ton of hydrochloric acid or 1 ton of an ethanol, right, which I don't need. So what I actually try to do is that I convert or try to actually transfer this particular side product to another company, where the second company use that as a raw material actually to try to do something else. And that is how these 133 companies, go tandem, hand in hand, and they do not actually produce any waste at the end of the day. And there is absolutely no chemical waste if you are actually in this particular plant. No smell at all, right? So that is the biggest inspiration for me. Can we try to implement that in chemistry in our laboratory, right? So like I said, a two thermodynamically unfavorable process, where in one side actually I can try to convert the CO2 into CO, which is very reactive. And on another side, actually, I try to convert the CH bond into a C reactive organometallic reagent in situ. If I am able to convert, if I am able to transfer a reactive CO gas into another reagent or another pot, then I will be able to actually do the chemical process, which are actually not possible in one single pot reaction. So I take a 2-chamber system, where in one chamber I try to produce a CO gas, which is a gaseous starting material, which can be trapped into a chamber B, and thereby I will be able to actually produce the product at the end, right? So that was the thought process, where we are able to actually show the CH carbonylation using CO2 as a CO gas, and make the corresponding carbonylation product without actually much trouble. So I do not want to spend much time with respect to the reaction conditions. You can actually go through our paper. So only thing I would like to show is that any methodology which we develop, we do actually a lot of control experiments to be absolutely sure that every parameter which we add in our reagent, in our reactions are necessary. And that is why actually we show all the control experiment to be sure that you indeed actually need the required reagent in chamber A, chamber B, and you do actually produce only 2 to 3 equivalent of CO gas. You don't need to actually use even more actually CO pressure. Okay, and that's 2 to 3 equivalent of CO gas which is produced in situ is good enough actually to do the carbonylation process. So the reaction is quite general. You can do a thalidomide, or you can actually synthesize the corresponding saccharin in quick time without any trouble. One could argue, so to synthesize a thalidomide or a saccharin, you have to go through this process, not necessarily, but look at the versatility this particular reagent gives. Let's say, for example, I have a different heterogeneous cycles at the backbone. Absolutely no problem. If this is really true, I should be able to actually apply this particular methodology in a very real-time synthesis, which I will come in a minute. So, like I showed you with the sp3-CH carbonylation, we can also do that with the CO2 as a carbonyl source rather than CO gas. So, like I said, so if you are able to show good functional group tolerance, then you should be able to apply that in a targeted synthesis at the late stage rather than actually from the beginning. Right? Say, for example, I take a CO2, 13C labeled to CO2 gas. I use the disilane as a reductant. Under the reaction conditions, I produce in situ 13C labeled to CO gas, which can be trapped actually by the second chamber. And in the second chamber, I purchase the telmisartan tablet, which is available in the supermarket or in the medical shop. You buy the telmisartan tablet, which is actually useful for the hypertensive patients, where people take every day the telmisartan tablet. This is a $1 million drug. It's a blockbuster drug in the market. You take this tablet, make it into small pieces, take the powder, put it inside your reaction mixture, do the reaction conditions, which was actually shown here, and trap the CO gas, which is actually coming from the CO2, and do the chemistry, and you are able to incorporate the CO 13C level to CO2 at the selective position, okay, without actually disturbing the other actually CH bonds. So which clearly indicates that I can do late stage functionalization, where the carboxylic acids are installed, where initial carboxylic acid is the C12 and the installed carboxylic acid is the C13, and this is going to be very useful, let's say, for example, in case if we want to do a level studies under in situ biological system. The same thing is possible not only with telmisartan. You can also actually buy chemfibrosil. This is another drug which is useful actually for low lipid level in the body. So this is still available in the market, and you can do the same process. You will be able to install the corresponding 13C label to carboxylic acid. So how does the reaction works? So as I said, actually we always curious about to understand the reaction mechanism. So we believe that the cobalt-2 initially go via ligand exchange and makes the NN coordination, followed by one electron oxidation from the cobalt-2 to cobalt-3, and then actually goes for the cyclometallation, which gives the intermediate C at the bottom, and then the CO insert between the metal and the carbon, followed by reductive elimination, gives the cobalt-1. And so to prove that indeed actually these intermediates are forming, so we have the crystal structure of the corresponding one, not with the CO gas, with the isonitrile, which is having the similar coordination behavior like CO gas. So which clearly indicates that indeed actually it is forming such kind of an intermediate, and the cobalt-1 further reoxidates into cobalt-2 with the silver-1, and so thereby you will be able to regenerate the catalyst. So, but the problem comes, right? So, if you look at the reaction conditions carefully, although I did not actually emphasize it actually before, but we know very well there is a problem here. There is a opportunity for us actually to improve. So, the opportunity is actually we use a stoichiometric amount of silver-1, which is very expensive on one side, and another side you also produce on the end of the reaction a stoichiometric amount of silver waste, right? If you are somehow able to convert that silver waste into something else, then it is useful, or convert the silver waste into a corresponding silver carbonate by a recycling process by treating with this nitric acid followed by aqueous sodium carbonate. You should be able to recycle the silver carbonate, and we did in fact in our case, in the case of carbonylation, the recycled silver carbonate was exposed to the reaction conditions. It also gives the expected product, but then the recycling process is again another couple of step process, right? Why do you need to do that? If you understand the reaction mechanism carefully, then you should be able to give a proper solution than going for the recycling process. What is the proper solution? So we know this cobalt-1 to cobalt-2, or here this cobalt-2 to cobalt-3 oxidation are actually one electron process. If this is really one electron process, then we should be able to actually do this one electron process, not with the stoichiometric amount of oxidizing agent like a silver-1 or a manganese-3. So we should be able to do this actually, let's say, with photocatalyst, right? So we know with the presence of light, you add a small pinch of photocatalyst. The photocatalyst is able to convert, let's say, the low-valent oxidation state, the high-valent oxidation state via single electron transfer process, right? If this is really true, then we should be able to do this tandem catalytic cycle, where the photosensitizer only able to do the metal oxidation from low-valent to high-valent, but it will not actually disturb the substrate. Right. So how do you actually choose the photocatalyst? There are numerous photocatalysts that are available on the market, right? So how do you know which photocatalyst is actually going to work for which reaction, right? So this is actually sometimes going to be extremely tricky. So that's why you need to actually understand your reaction mechanism very well. So you have to understand what is the redox potential of the corresponding cobalt-2 to cobalt-3, and you have to also understand the redox potential of corresponding cobalt-1 to cobalt-2. If you know the corresponding oxidation potential, then you will be able to choose the corresponding reduction potential actually comes from the oxidase photosensitizer. So based on the numbers, we are able to, let's say, shortlist a few photosensitizers, and we screened some of the photosensitizer, and we found the ruthenium-2 photosensitizer and the iosine photosensitizer are very effective for the cobalt oxidation from cobalt-1 to cobalt-2 or a cobalt-2 to cobalt-3. So with that, actually, we do some kind of a cooperative catalysis where we try to do the C-H annulation with the presence of photocatalyst without adding any stoichiometric amount of metal additives. And so that was able to actually show the corresponding annulation product. So I do not actually show the scope here. So this is how actually the proposed mechanism works, where the cobalt-2 initially go for ligand exchange, one electron oxidation becomes cobalt-3, and the sodium pyruvate will actually comes in, make the corresponding CH activation. Alkyne comes, insert between the metal and the carbon. You form the alkenyl intermediate, which goes for reductive elimination, gives a cobalt-1, and that cobalt-1 further actually oxidizes into the corresponding cobalt-2, which is going to be available for the next catalytic cycle. So how do we actually prove that? So as I said, we have isolated this intermediate actually for the corresponding cobalt-3, and we have also isolated this intermediate actually for the corresponding alkenyl intermediate with the CP star system, and that is why we believe our proposed mechanism is actually correct. We believe that. So that actually brings the CH functionalization contribution actually from our side, actually, especially with the high-valent cobalt. We have actually done wide variety of actually functionalization using the cobalt high-valent catalyst. So maybe in the last couple of minutes, I would like to show, although this is not actually comes under this particular topic, but this will be interesting actually for a wider audience, and that's one of the reasons I bring this particular few slides at the end of my talk. So polymers. So people actually always actually question whether it is a boon or a harm, right? So I think anything you see in our day-to-day life are all actually made up of polymers, right? So whether it is a plastic table or an equipment actually which is available on various front, so right from health sector actually to consumables actually to household items. So everywhere we see polymers. Without actually polymers, we cannot actually even think our life. But actually 60 years or 70 years down the line, there is absolutely no polymer was available, right? People do actually exist. People do actually live their life without actually any problem, right? So now with the polymer, we get used to it. I don't think actually we will ever actually go back to the prior era of 1950, right? So we have to live with this polymer, but now we need to also bear in mind that this is actually the what going to actually get as a side product, right? So you have actually a lot of advantage of using a polymer, but you do also throw out actually a lot of waste actually on an environment, and that is actually going to accumulate more and more and more. And that is what actually we learned actually during this pandemic, that we do disturb the nature, and the nature actually comes back hard on us to even stop us to have our regular life, right? That's what actually we all actually go through in the difficult times, right? So we continue to actually do this, so we need to actually find a solution. So who else actually will find a solution, right? So if you look at actually Carl Ziegler, who is Carl Ziegler? Carl Ziegler is an organometallic chemist, where he tried to work with an organometallic species, wanted to see a reactive organometallic species can actually try to make some sort of a carbon metal bond. That's all actually he tried to study in all his actually career, right? So that's when actually he tried to find this serendipitous polymerization, and that eventually gives a a very valid application actually to the human community. So if we as a chemist actually create a polymer, and we as a chemist also should be able to actually find a solution to recycle the polymer, right? One can also argue actually why the existing recycling process is not actually good enough, because the existing recycling processes are very expensive than the amount or the investment which you make for the polymer, right? So then what is the purpose of actually investing that particular money if I actually put 1 rupee to buy a polymer, if I have to actually put 10 rupee to actually recycle the polymer, right? And that is one of the reason as the recycling process through chemical way is quite important. So we thought actually it is quite interesting actually problem. We should actually contribute this particular problem. So we try to actually take our cobalt catalyst and see if we are able to, let's say, convert the polylactic acid or a polycarbonate or a polyester or even poly terephthalate. So we can be able to actually convert that into a monomer, right? So how do we do that? So the simple way to do is actually do the hydrogenolysis. When you actually do the hydrogenolysis, you break the link. When you break the link, you actually get the two different monomers. So on one front, actually people are worrying about how to convert the CO2 into methanol, and on another front, so it is a very well industrially known process. It's called Shell Omega process, where you take a epoxide, treating with the CO2, you will be able to actually form the corresponding carbonate, which is actually already available in industrial scale, and people actually try to produce in multi-ton scale of the corresponding carbonate. What are we going to do with this carbonate? So people tend to use this carbonate as a solvent, as a green organic solvent actually for organic synthesis. And people also convert, let's say, the carbonate into the corresponding, let's say, the hydrogenolysis product. If that is possible, I mean, with a cheaper catalyst, then it should actually solve majority of our problem. So let's say, for example, if I take a simple carbonate, we have seen actually quite a lot of actually well-defined CP stock cobalt catalyst, and this particular catalyst is very effective compared with, let's say, the other catalysts which we screen. And the catalyst loading, we can go up to 0.0001 mole percent, which clearly indicates that there is a lot of scope actually to convert this actually from academia to industry. So there they convert the carbonate into corresponding alcohol and methanol, and so this actually solves two problems. One, you can convert the alcohol carbonate based polymer into monomer, but at the same time you can also convert CO2 into a carbonate and carbonate into a corresponding methanol. This is the indirect way to convert the CO2 into methanol. So we do have a pretty good reactivity with our catalyst. So we do screen both cyclic as well as acyclic carbonate. It does actually gives the expected monomeric alcohol and the corresponding methanol. So then we take even more challenging problem. We buy the commercially available polymer and we try to expose to our reaction conditions. Indeed, it actually gives the expected compound. So then we decided why not actually to take material which are thrown out by the consumers after they use. Let's say, for example, CD disc, which are available in our own laboratory and which was not actually useful for us because it's already thrown out CD. And we take this CD disc, we cut it into a very small pieces and take these small pieces and put it in an autoclave and do the hydrogenalysis under the catalytic conditions which we established actually for the carbonate reduction. And when we try to do the reaction, so what we get is at the end of the reaction, so we get a yellow powder and we just filter it out and remove the solvent and we got the yellow powder in a very good actually quantity. And this yellow powder is nothing but the bisphenol A. This is the starting material which people used to actually use as a monomer actually to do the polymerization, which means you should be able to convert the polymer into a corresponding monomer without actually much trouble. And that is what actually we show under hydrogenalysis conditions. And this is much cheaper process than through a mechanical recycling, which is expensive. With that, actually, I conclude my talk. So, of course, all the work which I have shown to you here is not actually done by me. It is all actually done by my talented PhD students and postdocs. I owe a lot of actually respect and thanks actually to them, and especially so majority of the CH functionalization work which I shown today is actually done by Naharaju, which is standing there on the right side, actually top right, second one. And so the second important person I would like to actually thank is Deepthi Kalsi, who is sitting at the right side bottom. So they both are actually currently doing their postdoc in the Max Planck Institute in Germany, and a couple of actually other PhD students submitted their thesis. One defended the thesis, so the rest of the PhD students are currently working in our laboratory. And so I do thank the funding agencies. Actually, without funding, anything is not actually possible. We can dream a lot of things, but without money, it is just not actually possible to achieve. So I do actually thank all the funding agencies for their generous support. I thank you all actually for your kind attention. I will be happy to answer any questions if there is any. Thank you.
Friends, now the session is open for discussion. If you have any clarification, please ask.
Just a moment, actually. Yes, please go ahead. Yeah, sorry.
Good morning, sir.
Good morning.
Thank you for your wonderful presentation, sir.
You're welcome.
There has been a question on the Google Meet chat box, so I'm representing that question, sir.
Yeah.
It's quite interesting, wonderful session. The aromatic nitriles bar N oxide into beta acylation conversion is a great thing with cobalt system. What would be expected products with the aliphatic N oxide systems with allylic systems or an alpha beta unsaturated ketone system? Can you please brief on this? That's a question, sir.
So it is in fact actually possible. So people used to call that as a nitrone, because in the case of aromatic system we call it as an N oxide. In the case of aliphatic system, we can, let's say, convert the ketone into an imine and then imine into an N oxide. So in this imine N oxide, people used to call that as a nitrone. So and that is very much possible. We have not done it, but I think the other researchers from Germany actually done that particular work after our work. So it's because we at the beginning I had only 4 PhD students to work with. So and this topic was extremely competitive. So whenever we published, and there is another group actually started to take up that particular result, and they started to continue with that. I mean, it goes front and back, so I cannot complain about it, but that's very normal because we publish our work. So yeah, this was done already by some researchers from Germany. It is possible.
Thank you, sir.
Is there any other question? Anybody have any other question? Anybody have any other questions, please? So in the absence of any other question, then I do thank Professor Dr. Bhaskar for his excellent talk on cobalt-catalyzed C-H activation, of course, functionalization reactions. By spending his valuable time and sharing his expertise with all our participants. Definitely, I do hope his lecture is definitely would be of brainstorming. At least for some of you people may have take up something from Professor's lecture and to develop further catalyst for CH activation reactions and so on in organometallic chemistry. I am very much thankful to Professor on behalf of chemistry department and organizers for recent trends in chemistry 2021. Thank you very much, Professor, for sharing valuable time and giving us an opportunity to interact with you at this forum. Thank you very much.
Thank you, Prabhakar Nakli, for your kind words. I must actually say a couple of things. So one, especially for the students who are studying in Bharathiar University. So I was denied actually for an admission actually in Bharathiar University, right? So no, actually I take it in a positive way. So such is the standard actually the Bharathiar University maintained. Okay, so and I would like to actually see that actually continue in Bharathiar University. There were a lot of actually people who actually studied in Bharathiar University, actually went in several places and settled down. And I know actually personally quite a lot of actually people, including actually let's say Prabhakaran, Dr. Coimbatore actually from NIT Trichy, and many others. Okay, so so I wish actually all the students actually who are studying in Bharathiar University a very best actually for their research as well as actually their studies. And in case if I am of any help actually at any level, actually please feel free to contact me. Thank you very much. So I was actually quite nervous at the start of my actually talk because I'm not actually in Kanpur, I'm at my hometown, and I really do not actually know how much the internet actually be stable from my home. So although I used to complain to the students when I teach actually online that the students are not actually coming to online classes, now I see myself, I mean, how difficult it is actually if you are actually at home. When I stay at IIT, it's quite different. I mean, you have actually high bandwidth internet speed. I mean, you have absolutely no problem. But when you stay, let's say, in a remote place where you are not actually getting the good internet facility, so I do feel like for most of the students actually who stay at home and then study. So I mean, thank you again, Prabhakaran, actually for your invitation, and I wish you actually all the success actually for your conference. Thank you.
Thank you very much. Thank you. Thanks a lot. Thank you.
Yeah. Bye.
Thank you. Bye.
Thank you, sir. Audience, please note, kindly fill in the feedback form by 2 p.m. The next session is at 2 p.m. to 3:30 p.m. and the speaker is Professor Dr. G. Prabhushankar on the topic NHC LTMS in medicinal chemistry, catalysis and light emitting applications. Kindly join by 1:45 in Google Meet. For those who cannot join by Google Meet, please use the YouTube link. Thank you.